Vidhai, inspire, educate, change. I am Kishore from IIITDM Kancheepuram, Vidhai. Exams Vidhai, everything is possible. Exams Vidhai is a non-profit initiative by the students of IIITDM Kancheepuram to give free coaching and resources to students preparing for national level competitive exams like NTSE and NMMS. The topic that we are going to discuss about is laws of motion. In previous part 1, we have completed the introduction, the law of inertia, the first law of motion, the second law of motion, the third law of motion, and here we'll be discussing about the derivation of conservation of momentum, common forces, and as well as the mass versus weight criteria. Now, conservation of momentum. As in previous part, we have discussed that the total momentum after and before collision remains the same. Therefore, let us derive mathematically and prove whether the case is satisfied or not. Now let bodies A and B have mass m1 and m2 move with initial velocity u1 and u2 in a straight line, and we'll assume that u1 is greater than u2. Since u1 is greater than u2, there has to be a collision in some point of time. So let us assume there is a collision after a certain time interval t, and after collision both the body, that is body A and B, they tend to move in a straight line with velocity v1 and v2. Since now during the collision FA and FB, these are action and reaction forces. According to the Newton's third law of motion, we know that action is equal to reaction forces, that is FA is equal to minus of FB. And now coming here for FB, we know that F is equal to ma by Newton's second law of motion. Now we know the acceleration is equal to rate of change of velocity with respect to time. So similarly here we find that m2 is into v2 minus u2 by t, that is for v, where we discussed only about u2 and v2. The rate of change of velocity with respect to time gives you acceleration, and that is multiplied with m2, which gives fb. Similarly fa, we find v1 minus u1 by t as acceleration, and it is multiplied with m1 to give fa, and this fa and fb is substituted in this formula such that m1 into v1 by u1 by t minus m2 into v2 minus u2 by t. By cancelling t both sides and rearranging the term, finally we get m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2, which shows that the total final momentum of an isolated system is equal to its initial momentum, or simply we can say the momentum before collision is equal to the momentum after collision. Hence our case is proved. Now going through the few illustrations of conservation of momentum, let's assume the recoil of a gun. We need to find the recoil velocity of a gun. The velocity v2, the recoil of a gun, can be found using the law of conservation of momentum. Let m be the mass of a bullet and capital M be the mass of the gun. Similarly, the v1 be the mass of a velocity of a bullet and v2 is the velocity of a gun. Now, according to the law of conservation of momentum, m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. But initially the gun and the bullet is in rest position. Therefore, the u1 and u2 is 0. Therefore, the term in the left hand side becomes 0. Therefore, small m v1 plus big M v2 is equal to 0. Therefore, when rearranging the term, we find the velocity of the gun, that is equal to minus m into capital M v1. Therefore, the recoil velocity of the gun is equal to minus small m by capital M v1. Here, the negative sign shows that the v2 is in the direction opposite to v1. But we also notice that since the mass of the bullet is very lesser than the mass of the gun, the recoil velocity of the gun will be considerably smaller than the velocity of the bullet. Now collision. In collision, we may regard that we already knew that in elastic collision, the momentum before collision is equal to the momentum after collision, and that's what it's mentioned here. In the absence of any external force of colliding bodies such as force of friction, the system can be considered to be an isolated system. In an isolated system, the forces interacting the colliding will not change the total momentum of colliding bodies. Therefore, our collision is satisfied. Our law of conservation of momentum is satisfied. For example, if the collision of striker with a coin of carom or collision between the billiard balls may be quite instructive and steady of collision between elastic bodies. Now coming for the third example, that is explosion of a bomb. A bomb explodes into fragments with release of huge energy. With the release of huge energy, is now considered the body is at rest initially. and then it explodes, and the two fragments A and B into two fragments, that is A and B. As the momentum of the bomb was zero before the collision, the total momentum of two fragments formed after the explosion is also zero. For this reason, the two fragments will fly off in opposite direction, and the masses of two fragments are equal. Therefore, the velocity of the two fragments will also be equal in magnitude. Therefore, the law of conservation of momentum is satisfied. Common forces in mechanics. Based on the direction in which the forces act, they can be classified into two types, that is, like parallel forces, unlike parallel forces. Two or more forces of equal and unequal magnitude acting on the same direction parallel to each other are called as parallel forces. For example, the weight of every apple in a bag is the force of gravity acting on it vertically downwards. Therefore, the weight of the apples are parallel forces. Similarly, for unlike parallel forces, the two or more equal or unequal forces acting in the opposite direction parallel to each other, but they are acting in opposite direction. Those are known as unlike parallel forces. Now coming to torque, it's also known as momentum of force, and the torque is also known as rotational force. As the definition says, it is the rotating or the turning effect of force about a fixed point or fixed axis is called moment of force. Mathematically, torque is defined as Fd sin theta or Fr, that is R and D, it denotes the same value, that is the perpendicular distance between the fixed point and the fixed axis to the line of action of force. Suppose the force is acting in this, you can see here the pink line that denotes the action of force, and it is equally, that is the line of force, and that's the distance, and this is the fixed point. Therefore, this is the distance between them is known as R. Therefore, you can say that Fr sin theta, since you're bringing the angle into the picture. By convention, if the rotation is anti-clockwise, it is positive torque. If rotation is anti-clockwise, it's negative torque. As you say, since it is the pink line is above the fixed point of axis, so we get positive torque. If it's below here, downward somewhere, if it's acting, then it will be a negative torque. It is mainly focusing on the direction of it. Example: a person is pushing a closed door is applying a static door because the door isn't rotating despite of force applied. And the second example is pedaling a cycle. There are various applications like seesaw, wrenches, gyroscope, pendulum, parachute is applying torque when swinging. The principle of momentum. According to this principle, in equilibrium, the sum of anti-clockwise moments is equal to the sum of clockwise moments. This is somewhat similar to the law of conservation of momentum, but there where the momentum takes place, and here we are including the moments. The moment is nothing but torque. To illustrate this principle, let's consider that D1 and D2 is the uniform rod length of D1 plus D2 is resting on a knife. The knife is nothing but this arrow, and let two forces F1 and F2 such as that this F1 is greater than F2. Therefore, when 2 tends this direction to move clockwise, whereas F1 turns to move the rod anti-clockwise. Therefore, the F1 causes anti-clockwise movement, F2 causes clockwise movement. That is F2 into D2. And anti-clockwise movement is F1 into D1. That is according to the torque formula. Here we are finding that. And in equilibrium, we can say that the clockwise momentum is equal to anti-clockwise moment. Therefore, this tends to be in a straight line. This illustrates the principle of momentum. Now coming to impulse. We sometimes encounter examples where a large force acts for a very short duration of time, producing a finite change in momentum of body. For example, if a ball hits a wall and bounces back, then the force on the ball by the wall acts in a very short time. When they are two in contact, it acts in very short time. The short force is known as impulse. Simply, we can define them. That is the product of force and time, which is the change of momentum, which is the measurable quantity, and this product is called impulse. That is, force into time is known as impulse. That is equal to change in momentum, nothing else. That's delta p is equal to, we can say that impulse is equal to delta p as well. That is the change in momentum. But here we can say f into time duration, that is delta t. Now, what is impulsive force? The impulsive force, the large force acting for a short time for a finite change in momentum, is called impulsive force. Now, coming to the most important force, that is known as gravitational force. The gravitational force is a central force which depends only on the position of test mass from the source mass, and always acts in the line joining in the center of two masses. According to the law of gravitation, we know that force is directly proportional to m1 into m2 and is inversely proportional to the r square, that is the distance between the center of masses. To remove the constant of proportionality, we bring g, which is the gravitational forces. Each body in this universe attracts other bodies towards itself with a force known as gravitational force. The gravitational force is a central force which depends only on position of test mass from the source mass and always acts in a line joining the center of two masses. Now let's assume the m1 is the source mass and m2 is the test mass, and we know that according to the law of gravitation, F is directly proportional into m1 into m2 and F is inversely proportional into the distance between the center of masses. Now in order to remove the proportionality sign, we bring in G, which is known as gravitational constant. This error, it should be an universal gravitational constant. That is, G is equal to 6.673 into 10 to the power minus 11 meter cube per kg per second square, and this is the SI unit of G value. This force is generally attractive in nature and it is independent of medium existed. Wherever you go, you experience this G, the gravitational force. Now, for example, we may notice that how an apple falls from a tree towards down, only downwards, and then why the moon revolves around the earth. This is all monitored by the universal law of gravitation. Now, the relationship between G and G, a small g and capital G. The small g is known as the acceleration due to gravity, and g is anyways the universal gravitational constant. Now, let a small object have placed in the surface of the earth if the mass of the small object is m, and then according to the Newton's second law, we know that F is equal to mg. This is since acceleration, since gravity is coming to play, instead of a, we use small g here. That is acceleration due to gravity, nothing more else than that. And mass of the earth is me. And we know that according to the universal law of gravitation, we have found in the previous slide that F is equal to G into me, that's me is the source and m is the test point, that is into r square, the distance between the me and m bodies. From the equation 1 and 2, we make comparing them, where the small m get cancelled out and we find the value of G. And here we may notice that the G is inversely proportional to radius of earth. Therefore, we may conclude that the more inside the earth you go, the greater the value of G it is. Mass versus weight. Mass, it is the quantity of matter contained in the body. It remains constant no matter where you go. Wherever you go, the amount of mass in your body will remain the same. Whereas weight, it depends on the gravitational force exerted at that position at that time due to Earth's gravity. That is, it varies from place to place. Now, apparent weight. The actual weight at that point of time due to gravity is known as apparent weight. Part of NCERT and in our board exams we may encounter this problem, that is apparent weight variation in lift problem. That is, this is the lift and the person is inside the lift, and if the lift is moving upward, what is the force acting? Total force, that is F net is equal to R minus mg. The negative sign denotes that it's acting in the negative direction since the lift is moving upward direction. But the mg, that the actual force due to the gravitational force acting downward, that is the negative sign, nothing more in that. And now we know that apparent weight is equal to m is equal to g plus a. Since you're moving top, you're adding even the acceleration as well as the gravitation, so that the apparent weight when you're going towards upwards, your apparent weight increases. Similarly, when you're going downwards, the apparent weight decreases. That will become g minus a. And similarly, mg minus a, since here r is going upward direction and the lift is falling downwards, that time you get negative here. Now, when the lift is at rest, when there is zero acceleration, then you will get the original weight. That is, due to the Earth's gravity, you get your original weight when the lift is at rest. That is similarly what when you're outside the lift, r is equal to mg, and when you're inside the lift, r is equal to mg, provided the lift should be at rest. The lift during free fall, that is acceleration is equal to g. Therefore, your weight will become completely zero, because the acceleration is equal to the acceleration due to gravity. Therefore, by substituting them, you get 0. Therefore, weight is equal to 0, and you may feel weighing less when the lift is at free fall. But this condition doesn't happen. But if it happens, you may feel weightless, weight 0 during the lift is at free fall. Well, that's the end. Thank you for attending. Hope you all like the presentation. I hope it was very informative and would be helpful for upcoming examinations. Thank you. Please do check the description below for extra questions and lecture notes for each chapter. Thank you.